Something shows up in telescope images on July 1st, 2025. Atlas survey station in Rio Hurtado, Chile, catches it first. The object is magnitude 18, faint, moving against the stars near Sagittarius. The speed is wrong, 61 kilometers per second relative to the Sun, coming in from interstellar space. 3.5 astronomical units from Earth when detected, 4.5 from the Sun. Not a planet, not an asteroid. A visitor from outside, tearing through our solar system at 220,000 kilometers per hour. They call it 3I Atlas. The third confirmed interstellar object ever observed. The I stands for interstellar. The comet was passing in front of the galactic center, lost in dense star fields. By the time someone flagged it, 3I Atlas had been screaming toward us for weeks, maybe months, undetected. The trajectory is hyperbolic. It will not orbit. It will not return. This thing came from somewhere else, swung past our sun, and it is gone forever. Then, Hubble Space Telescope images on July 21st, 2025, show a teardrop-shaped coma, dust and gas streaming off the nucleus. It is a comet, and it is active. The nucleus diameter is somewhere between 320 meters and 5.6 kilometers, most likely under 1 kilometer. Small target, massive distance, huge implications. By August 6th, James Webb Space Telescope points its near-infrared spectrograph at 3I Atlas. What it sees changes everything. 1. I Oumuamua, and 2 I Borisov, the only other confirmed interstellar objects, did not look like this. 3. I Atlas is an outlier. The spectrum shows water ice, carbon monoxide, carbonyl sulfide, dust, but carbon dioxide dominates. The outgassing is enhanced on the sunward side, exactly where you would expect solar heating to drive sublimation. But why so much carbon dioxide? If you value documented space exploration and astrophysics history like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. Also, this script is researched and factual, using sources from NASA Science published July 3rd, 2025, and the Architive preprint server paper by Martin Cordner and collaborators published August 25th, 2025, along with ESA official documentation from their Planetary Defense Coordination Center and the Max Planck Institute for Solar System Research press releases from October 2025. Now back to the information. The James Clerk Maxwell Telescope measures hydrogen cyanide production on September 7th at 1.5 times 10 to the 25th molecules per second. A week later, September 14th, the rate climbs to 4.5 times 10 to the 25th molecules per second. 2 kilograms per second of cyanide escaping into space. The coma stretches 180,000 kilometers across on September 15th. Asymmetric. Elongated away from the sun, a visible dust tail extends 100,000 kilometers. It breaks apart under ultraviolet light, releasing nickel atoms and carbon monoxide. That could explain high early activity while the comet is still far from the sun. It could also explain some of the carbon monoxide detected in the coma. Observations at wavelengths between 342.5 and 550 nanometers. The data reveals spatial structure. Nickel is distributed uniformly around the nucleus. Cyanide appears in 2 distinct jets. Not uniform, 2 jets. This is the first time anyone has used Keck for this kind of integral field spectroscopy on a comet. The jets suggest active regions on the nucleus surface, specific spots where volatiles are escaping. Spin axis orientation matters, surface composition matters. 3. I Atlas is not a uniform ball of ice. 40 kilograms per second of water. But that water is not coming directly from the nucleus. The water ice grains in the coma are sublimating at a distance between 4,000 and 10,000 kilometers from the nucleus. The grains were ejected by carbon dioxide and carbon monoxide outgassing. Then they started sublimating on their own. Water ice grain size is under 1 micrometer, fine particles. Probably amorphous ice, not crystalline, though crystalline cannot be ruled out. Carbon monoxide levels are lower than expected for an Oort cloud comet. Lower carbon monoxide suggests thermal processing. This object has been close to a star before, maybe its parent star, maybe others during billions of years drifting through the galaxy. Heat altered the surface. Volatiles escaped. What remains is carbon dioxide rich and depleted in carbon chains. MDM Observatory and Very Large Telescope search for dicarbon and tricarbon in August 2025. None detected. The comet is highly depleted in carbon chain compounds. Dicarbon to cyanide ratio suggests 3I Atlas is one of the most carbon chain depleted comets ever known. This is not normal for solar system comets. Long period comets from the Oort cloud are rich in carbon chains. Dicarbon makes them glow green. 3. I Atlas does not glow green. The depletion could be primordial, formed that way, or it could be radiation damage. cosmic rays bombarding the surface for billions of years, breaking down organics, converting carbon monoxide to carbon dioxide. The crust is estimated at 15 to 20 meters thick. Radiation-processed material, insulating the pristine interior. Hyperbolic excess velocity breaks down into galactic coordinates. U component is negative 51 kilometers per second, moving away from the galactic center. W component is positive 18.5 kilometers per second, moving upward through the galactic plane. That W velocity is high, too high for thin disk objects. Thin disk stars and comets have low vertical velocities, confined near the galactic plane. Thick disk objects have high vertical velocities, orbiting in tilted paths above and below the plane. 3I Atlas belongs to the thick disk. The thick disk formed 7 to 10 billion years ago. Stars there are metal poor compared to the Sun. Lower abundances of elements heavier than helium. This comet did not form in a young stellar system like ours. Matthew Hopkins, astronomer at Oxford, defended his doctoral thesis on interstellar objects 1 week before 3. I Atlas was discovered. His Ototahai Oxford model predicts properties of interstellar visitors based on galactic dynamics and stellar populations. The model estimates 3I Atlas formed around a thick disk star. Statistical confidence is 68% that the comet is between 7.6 and 14 billion years old. 2/3 probability, it is older than the solar system. Our sun is 4.6 billion years old. Earth is 4.54 billion years old. 3. I Atlas likely predates both. By 3 billion years, maybe more. Formation epoch was during cosmic noon, the peak of star formation in the universe, roughly 8 to 12 billion years ago. If 3I Atlas formed around a thick disk star 8 billion years ago, it has been drifting through interstellar space ever since. A September 2025 study by Yi-Yang Guo traces possible encounters. The comet may have passed within 1 parsec, 3.3 light years, of 25 known stars in the past 10 million years. Gravity assists from those encounters altered its velocity. Close passes through molecular clouds could have done the same. Reconstructing the exact path is impossible. Too much time, too many perturbations. The parent star is unknown and will remain unknown. What does the composition tell us about formation conditions? The high carbon dioxide ratio suggests 2 possibilities. First, intrinsically carbon dioxide-rich nucleus, formed close to the carbon dioxide frost line in the parent protoplanetary disk. Beyond that line, carbon dioxide condenses. Water ice is further in. Carbon monoxide is further out. If 3I Atlas formed right at the carbon dioxide frost line, high carbon dioxide makes sense. The second possibility, radiation damage, billions of years in interstellar space, cosmic rays penetrating the surface, carbon monoxide converts to carbon dioxide. Water sublimates or gets locked under an insulating crust. The crust suppresses water outgassing. Carbon dioxide sublimates more easily. Both scenarios are consistent with observations. Nickel tetracarbonyl and iron pentacarbonyl are trace compounds. They form when metal atoms interact with carbon monoxide in cold, low-pressure environments. Interstellar space qualifies. If 3I Atlas has been exposed to cosmic rays and interstellar carbon monoxide for billions of years, metal carbonyls could accumulate in surface layers. When solar heating starts, the carbonyls sublimate first. Ultraviolet light breaks them down. Nickel and iron atoms fluoresce. The high nickel to iron ratio early in the mission fits this model. Nickel tetracarbonyl is more volatile than iron pentacarbonyl. It sublimates at lower temperatures. Nickel appears first. Mars flotilla gets the closest look. October 3rd, 2025. Mars Reconnaissance Orbiter, MAVEN Orbiter, ExoMars. Trace Gas Orbiter, UAE Hope Orbiter. Distance to the comet is 29 million kilometers. ExoMars Trace Gas Orbiter uses its color and stereo surface imaging system, CASIS, 5-second exposures. The comet appears as a fuzzy white dot moving downward near the center of the frame. Mars Express tries with shorter exposures, 0.5 seconds maximum, too short. The comet does not show up clearly. Scientists combine multiple frames, stacking them to increase signal. They also attempt spectroscopy with Omega, SpyCam, and Nomad instruments. Whether the coma was bright enough for spectral characterization is uncertain. Analysis continues for weeks. ExoMars. Trace Gas Orbiter is orbiting Mars, moving fast. Its exact position and velocity are known. CASIS was designed to photograph the Martian surface a few hundred kilometers below. This time, it pointed at the sky, catching 3.5 Atlas against background stars. The parallax is significant. Mars is 10 times closer to the comet than Earth was in early October. Triangulation between Earth-based observations and Mars-based observations improves the predicted trajectory by a factor of 10. The uncertainty in the comet's position drops dramatically. This is the first time astrometric measurements from a spacecraft orbiting another planet have been officially submitted to the Minor Planet Center database. The database archives asteroid and comet observations from telescopes, radar stations, and spacecraft worldwide. Planetary defense teams need accurate trajectories. 3. iAtlas poses no threat, but the method works. Future objects might. SOHO spacecraft, positioned at the Earth-Sun Lagrange point, captures the comet passing through its field of view. Solar wind interactions, magnetic draping structures around the coma, ion tail formation. These observations are valuable but brief. October 29th, 2025, perihelion, closest approach to the Sun, distance is 1.36 astronomical units, 203 million kilometers, just inside the orbit of Mars. Solar heating peaks, volatile outgassing increases, dust production spikes. This is when the comet is most active. Whether the spacecraft actually encountered the tail depends on exact geometry and tail brightness. Data analysis is ongoing. Hera spacecraft, also en route to its asteroid mission, potentially crosses the ion tail between October 25th and November 1st. Same situation, potential detection, confirmation pending. Primary goal, study Ganymede, Callisto, Europa. Arrival at Jupiter is years away. Right now, late October 2025, JUICE is in cruise phase. The spacecraft is passing through the inner solar system, using its main high-gain antenna as a heat shield. Designed for the cold environment of Jupiter, JUICE must protect sensitive instruments from intense solar radiation. Remote sensing instruments are not supposed to be active during this phase. Thermal constraints. But iAtlas is a once-in-a-lifetime opportunity. Between November 2nd and November 25th, 2025, JUICE observes the comet. PP particle environment package with neutral atom sensor. Distance to the comet is approximately 0.5 astronomical units, 75 million kilometers, farther than the Mars spacecraft were in early October, but JUICE is observing just after perihelion. The comet is in a highly active state. Outgassing is strong. The coma is bright. The tail is extended. Conditions are optimal despite the distance. Operational challenges are significant. JUICE and 3i. iAtlas are traveling in different directions. The comet is moving at 220,000 kilometers per hour. JUICE is following its own trajectory. Pointing requirements are strict. The spacecraft can only look directly at the comet for 30 minutes per day. Longer exposures risk overheating. The spacecraft must slew to keep the sensitive side in shadow. Only PP can measure continuously for 12 days because its field of view is wider and does not require precise pointing. Every other instrument gets 30-minute windows. Ground-based telescopes cannot observe these lines because Earth's atmosphere absorbs them. Space-based submillimeter instruments like SWI can. The goal is to measure water production rate directly. Compare it to carbon dioxide production. Test whether the high carbon dioxide to water ratio holds at perihelion when the comet is most active. Water sublimation should increase with solar heating. Does it catch up to carbon dioxide? Or does carbon dioxide still dominate? Ultraviolet emission from hydroxyl radicals, carbon monoxide, atomic oxygen. These species fluoresce under solar ultraviolet radiation. The tail structure reveals outflow patterns, dust to gas ratio, fragmentation events, rapid brightness changes. UVS on JUICE is the fifth in a series. Previous versions flew on Rosetta, New Horizons, Lunar Reconnaissance Orbiter, Juno. Proven technology, high reliability. MAGIS, near-infrared spectrometer, cannot observe the critical 6.1 micron water bending mode. That line is outside MAGIS bandwidth. The Emirates Mars infrared spectrometer on HOPE orbiter at Mars could have detected it in early October, but Mars observations focused on different wavelengths. JWST mid-infrared instrument can observe 6.1 microns, but JWST cannot observe 3. iAtlas between August 25th and December 9th, 2025, due to sun angle constraints. JUICE MAGIS operates in shorter infrared wavelengths. It can detect water ice absorption bands, carbon dioxide emission, carbon monoxide, dust continuum, spatial maps of coma composition, differences between sunward and anti-sunward sides. Jet structures. MAGIS provides context for the other instruments. Changes over time. Growth of the tail, evolution of the coma. These images complement the spectroscopy. PEP can operate for 12 days straight because its field of view does not require precise pointing. Continuous coverage provides long-term context. Are there periodic variations? Rotation of the nucleus modulates outgassing. Active regions spin in and out of sunlight. Brightness pulsations. PP might catch them. The spacecraft uses its high-gain antenna as a thermal shield. Data transmission requires the high-gain antenna pointed at Earth, but pointing at Earth means exposing the sensitive side to solar radiation. Unacceptable. Instead, JUICE uses the medium-gain antenna, lower data rate, much lower. Additionally, Earth and JUICE are on opposite sides of the Sun in November. The communication path goes around the Sun. Signal-to-noise drops. Distance increases. Bandwidth is limited. The spacecraft stores the data on board. February 2026. JUICE will be farther from the Sun. Thermal conditions improve. The high-gain antenna can point at Earth without overheating. Data downlink begins. High-speed transmission. The observations are trapped on board for 4 months. Delayed souvenir photo. Olivier Huitas, ESA project scientist for JUICE, explained in October 2025 interviews that the campaign was unexpected. JUICE is in cruise phase. No payload activities were planned. Thermal constraints prevent normal science operations. But the uniqueness of 3I Atlas justified the risk. The team prepared special observation planning, coordinated efforts between flight dynamics, science teams, instrument teams. Challenges that are usually negligible had to be tackled. Margins reduced as much as possible. The observations proceeded. Success is not confirmed until February 2026, when the data arrives. Carbon dioxide sublimates more easily, escaping through the crust. Perihelion heating should erode the crust. Fresher ice underneath gets exposed. Water production might spike post-perihelion. JUICE observes in November, 2 weeks after perihelion. Perfect timing to catch this transition. If water production increases sharply, the crust hypothesis is supported. If carbon dioxide still dominates, the nucleus is intrinsically carbon dioxide rich. Second, isotopic ratios. UVS might detect deuterium to hydrogen ratio in water. Deuterium is heavy hydrogen. The ratio in comets reflects formation temperature in the protoplanetary disk. Cold formation, high deuterium. Warm formation, low deuterium. 3. I-Atlas formed around a thick disk star. Thick disk stars are metal poor. Does that affect deuterium to hydrogen ratio? Carbon isotope ratio in carbon dioxide was measured by JWST in August. Carbon-12 to carbon-13 ratio is at least 63. That is high. Solar system comets have lower ratios. Interstellar comets might differ. More isotopic data constrains formation conditions. These species have different sublimation temperatures. They appear at different heliocentric distances. Ammonia and methane are very volatile. If they are present, they sublimate early. Methanol and formaldehyde are less volatile. They appear closer to the sun. Hydrogen cyanide breaks down into cyanide radicals, already detected by ground telescopes. Direct detection of hydrogen cyanide by SWI would confirm the parent molecule. The volatile inventory reveals the chemical environment in the parent protoplanetary disk, oxidation state, carbon to oxygen ratio, nitrogen abundance, sulfur species, all clues to formation conditions. 3. I-Atlas reached 3 astronomical units on August 15th inbound. It will reach 3 astronomical units again on January 11th, 2026 outbound. Fragmentation could occur in that window. JUICE observes in November. If fragmentation happens, brightness surges. Dust production spikes, multiple condensations in the coma. Janus images would show it. Spectroscopy would reveal composition changes. Fresher interior material gets exposed, pristine ices, higher water content. The chemistry changes. Active regions might correlate with surface features, color differences, albedo variations. These details inform models of nucleus structure. Is it a single body, a contact binary, rubble pile, differentiated, or homogeneous? The jets are windows into the interior. 2. I. Borisov, in 2019, active comet, carbon monoxide, rich, fragmented. Now 3. I-Atlas, more active, possibly larger, definitely older, carbon dioxide rich, nickel emissions, ancient origin from the thick disk. The age is staggering, 7 to 14 billion years old. The universe is 13.8 billion years old. 3. I-Atlas witnessed cosmic noon, peak star formation 10 to 12 billion years ago. It is a fossil carrying chemical signatures from that era. Now briefly, it passes through sunlight. In 2 months, it is gone, back into interstellar space, never to return. This script uses data from the European Space Agency's official publications from October and November 2025, NASA's Comet 3, I-Atlas mission page, updated throughout 2025, peer-reviewed and preprint papers from A.R. Cardiff, including Hopkins and collaborators published July 2025 on Comet Age and Origin. Cordner and collaborators published August 2025 on JWST spectroscopy. And Hugendam and collaborators published October 2025 on Keck integral field spectroscopy. All facts are documented and sourced. Now back to the information. The data does not fit standard models. China's Tianwen-1 orbiter at Mars observed in early October. Images show coma and tail. Perseverance rover at Jezero crater captured 3US. I-Atlas on October 4th. Faint smudge. Distance 75 million kilometers. Lucy spacecraft observed in September from 386 million kilometers. Another trajectory data point. Ion tail stripping. Solar-wind interactions. Punch mission observed with wide-field coronagraph. Stereo mission from September 11th to October 2nd. Movie-like coverage. Day-by-day evolution. Test provided high-cadence photometry. No fragmentation reported. Nucleus appears stable. Until then, speculation. Predictions based on other observations. If the comet remained active post-perihelion, JUICE should detect strong carbon dioxide emission. Water production might increase if the crust eroded. SWI might measure water to carbon dioxide ratio closer to 1:1 instead of 1:8. That would support the crust hypothesis. If the ratio stays at 1:8, the nucleus is intrinsically carbon dioxide rich. Formation near the carbon dioxide frost line. Radiation processing in interstellar space. Isotopic ratios from UVS would be groundbreaking. Deuterium to hydrogen in water. Carbon-13 to carbon-12 in carbon monoxide and carbon dioxide. Nitrogen-15 to nitrogen-14 in cyanide. Each ratio tells a story. Formation temperature, parent star metallicity, cosmic ray exposure, galactic environment. If jets are visible in infrared wavelengths, they can be traced back to source regions on the nucleus. The nucleus is not resolved, but the jets are. Jet morphology changes with rotation. Tracking jets over hours reveals spin period. Comparing jets between different species, carbon dioxide jets, water jets, dust jets, reveals nucleus layering. Differentiation, volatile concentration, the interior structure of an interstellar comet. Never before observed at this resolution. Dust grains with embedded metals, on the metal abundances constrained by parent star metallicity. Thick disk stars are metal poor. Sodium and iron should be depleted relative to solar system comets. Nickel to iron ratio should be high. That matches August observations. Consistency supports the thick disk origin. The spectroscopic lines change, fresh ice exposed, water production spikes, volatile organics, previously locked inside escape, ammonia, methane, ethane. The volatile inventory suddenly becomes much richer. This happened with TUI Borisov. Fragmentation around March 2020 revealed a subcomponent. Brightness increased, the spectrum changed. 3I Atlas has not fragmented yet as of late November 2025, but it could. Thermal stress peaks days to weeks after perihelion. Subsurface ice sublimates, pressure builds, fractures propagate, the nucleus splits. If JUICE caught this, the data would be priceless. JUICE observes just after. The comet is still bright, still active, and JUICE has instruments Mars spacecraft lack: submillimeter spectroscopy, ultraviolet spectroscopy, near-infrared imaging spectrometry, particle environment mapping, multi-instrument synergy. Each measurement complements the others. The whole is greater than the sum. 3. I-Atlas has carbon dioxide to water around 8. If this reflects formation conditions, the comet formed beyond the water frost line but near the carbon dioxide frost line, maybe 3 to 4 astronomical units from the parent star. Thick disk stars are lower mass. That places the formation zone in the right range. Water sublimated. The crust became carbon dioxide dominated. Perihelion heating erodes the crust. Interior material gets exposed. Water production increases. February 2026, data will clarify. Both form from metal atoms reacting with carbon monoxide in cold environments. Long interstellar exposure produces these compounds, consistent with age estimates. Hydrogen cyanide is common in comets. It sublimates at moderate heliocentric distances, breaks down into cyanide radicals under ultraviolet light. The cyanide production rate in 3I Atlas is similar to 2I Borisov and solar system comets. No anomaly. Hydrogen cyanide forms from nitrogen and carbon. Both elements are abundant in protoplanetary disks, nitrogen mostly in ammonia, carbon mostly in carbon monoxide and methane. Gas phase chemistry converts some to hydrogen cyanide. Grains absorb it. Comets trap it. Hydrogen cyanide is a baseline diagnostic. Its presence confirms active volatile sublimation. Its absence would be strange. Possible explanations: formation in a carbon monoxide rich, carbon chain poor region, or radiation processing destroyed carbon chains. Cosmic rays break chemical bonds. Organics decompose. Simple molecules dominate. Complex molecules are lost. The depleted state supports ancient age and long interstellar exposure. Fresh solar system comets from the Oort cloud have carbon chains. They spent billions of years in cold storage, but inside the solar system. Radiation exposure was lower. 3. I-Atlas spent billions of years in true interstellar space. Galactic cosmic ray flux is higher. Destruction is more efficient. 3. I-Atlas will be observable from Earth again starting December 2025. It reappears from behind the sun. Distance is increasing. Brightness is fading. Ground telescopes with large apertures can still detect it. Keck, Gemini, VLT, JWST. Monitoring continues into 2026. JWST scheduled for additional observations in December 2025. Post-perihelion spectroscopy. Compare with pre-perihelion data. Has the composition changed? Is water production higher? Are new species detected? Hubble until late 2026. JWST until mid-2027. By September 2027, even JWST loses it. 3. I-Atlas fades into interstellar space. Mission accomplished. 6 years from now, the mission proceeds. 3. I-Atlas was a bonus, an unexpected opportunity. JUICE delivered, or will deliver, once the data arrives. The spacecraft returns to its primary mission. Jupiter system exploration, Ganymede, Callisto, Europa, icy moons, subsurface oceans, habitability. But for 4 weeks in November 2025, JUICE was a comet hunter, observing the oldest comet ever detected, a visitor from the dawn of the galaxy. Using spacecraft at Mars or elsewhere in the solar system for parallax measurements improves precision. The Minor Planet Center database now includes astrometry from a Mars-orbiting spacecraft. First time. Proof of concept. Planetary defense teams take note. If interstellar objects can be this large, the population is richer than expected. Detection bias favors large objects. Small objects are hard to spot. But if large objects are not rare, small objects are abundant. Every star system ejects comets during planet formation. Billions of stars. Trillions of comets. The galaxy is full of them. 3 I-Atlas is one sample. A single data point, but a compelling one. Vera Rubin Observatory starts operation soon. Legacy survey of space and time. 10 years. Deep imaging, rapid cadence. Predictions suggest 50 interstellar objects detectable over the survey lifetime. Maybe more. Each one is unique. Different composition, different age, different origin. Some from the thin disk, some from the thick disk, some from the halo, some from nearby star systems, some from distant star systems. Population statistics will emerge. Trends in composition, trends in size, trends in activity. The field of interstellar object studies will mature. 3. I-Atlas is the beginning. We infer them. Comets are direct samples, physical material from those disks. 3 I-Atlas formed around a thick disk star 7 to 14 billion years ago. That star had a protoplanetary disk. Planets might have formed. Maybe they did not. The comet was ejected. Gravitational scattering, planet-planet interaction, or maybe stellar encounter. Close pass by another star. The comet's orbit was perturbed. Ejection velocity exceeded escape velocity. It left the system, drifted through interstellar space for billions of years, encountered other stars, gravity assists changed its velocity, slowly, randomly. Eventually, it entered the solar system, hyperbolic trajectory, one pass, gone forever. If the parent star was solar mass or smaller, it might still be shining, but we cannot identify it. The comet's path is untraceable. Too many encounters, too much time. The parent star is anonymous. The system is anonymous. 3. I-Atlas is a messenger with no return address. Rotation period, isotopic ratios, dust to gas ratio, fragmentation or stability. All these are possibilities. Confirmation requires February 2026. Data downlink, analysis, publication. Until then, we wait. The observations are done, the spacecraft is healthy, the data is stored, patience. Before Earth existed, before the solar system existed, it witnessed the galaxy in youth, star formation at peak, supernovae frequent, metal enrichment proceeding, the thick disk assembling. It survived, unchanged, frozen. Now, briefly, we see it, we measure it, we learn from it. This is not abstract. This is direct contact with deep time, a 7 billion-year-old object, older than half the universe's current age, passing through our neighborhood. We built machines to observe it, Hubble, JWST, JUICE, dozens of ground telescopes, spacecraft at Mars, rovers on Mars, all pointed at one small, faint comet. Because it is not just a comet, it is history, it is chemistry, it is the galaxy's story written in ice and dust. The picture will be incomplete, some questions will remain unanswered, but it will be the most detailed view of an ancient interstellar comet ever obtained. JUICE, designed to study icy moons around Jupiter, delivered observations of an icy comet from beyond. The instruments worked, the planning worked, the risks paid off, the thermal constraints were managed, the spacecraft survived. The data is coming. Moving outward, speeding away at 250,000 kilometers per hour. By January 2026, it will cross 3 astronomical units outbound, the same distance it crossed inbound in August 2025. The symmetry of solar approach and departure, the comet dims, the tail fades. By mid-2026, only the largest telescopes can see it. By late 2027, it is gone, invisible, back into the dark. Back into interstellar space, back into the galaxy. It will drift for billions more years. Maybe it will pass another star. Maybe it will be perturbed again. Maybe it will visit another planetary system. Or maybe it will drift forever, alone, silent, a fossil of cosmic noon, a relic of the thick disk, a messenger from deep time. We caught it for a moment. JUICE observed it at peak activity. The data is trapped on board. February 2026. Then we know. Until then, speculation ends. The facts arrive. The comet reveals its secrets. What it took 7 billion years to preserve, JUICE will decode in one observing campaign. That is the promise. That is the science. That is why we build spacecraft. That is why we point them at faint, distant, ancient objects. Because the universe is old. The galaxy is vast. And sometimes, just sometimes, something from out there passes through. And we are ready.